next talk, we stay in the area of iPhones and reverse engineering. And let's welcome Luca, Rashna, and Bruno, and give them a warm round of applause.
Hey everyone, so today we're going to talk about another walled garden. I hope you were there for the previous talk, which I thought was very good. We will also talk about an Apple walled garden, this time the baseband. This is not only on the iPhone, because we will talk about a baseband that is made by Qualcomm, that is in a lot of phones, you will see. And yeah, so we are three researchers from a small company in Berlin called Security Research Labs, and we usually concentrate on everything hardware and telco. So today we looked at the baseband of the iPhone. But to understand why we took a look at that, you have to understand where we are coming from a bit. So we did a lot of fuzzing. We do a lot of fuzzing in general. And we had worked before with things like firmware, which is a very nice framework to fuzz basebands. And this is practically the state of the art. And they themselves say in their paper that it is not possible to emulate hexagon-based basebands. And this is basically the talk that we have today. So we need to understand what hexagon means, also what a baseband is. So for those people who don't know, the baseband is the cellular modem, so everything that is telecommunication related in your phone usually is handled by that chip. And yeah, hexagon is a specific architecture. So what we try to do here is to create a bit more transparency around hexagon in general. Also do some enabling for you people actually to do some vulnerability research and then secure these chips even more. So we will release some tooling. It is actually already online if you have the link that I will provide later. So the Qualcomm baseband itself is another chip. So you have the main, what you would call CPU. In this case, we call it application processor. And there's a separate processor, and this separate processor is what we will be talking about today. So the interesting part of this is that the attack surface is quite big. So this chip is doing a lot of stuff. For example, it's doing like everything that is over the air. So the threat surface would be over the air. Everything that you would have 5G, 4G, even GPS and things like this will be received by the baseband processor and processed. Intercommunication, so there's also a threat surface between the application processor and the baseband itself, because there is some communication going on, obviously. And also there's a diagnostics interface. All of this, 2 and 3, have been researched before, but now you will see that it will be easier to do that. To understand also why this is important for security, you have to imagine that there's a lot of possibilities of hacking if you have access to this baseband. Like it has access to GPS and it has a whole HTTP stack. It runs its own OS. So if you are able to have code execution on this, you can geolocate people, you can listen into calls, you can read the SMS of these people. So the security of these chips is very, very important. The previous research that was around this is very interesting, and there has been some reversing since a long time around hexagon itself, around the protocols that the baseband chip can be talked to. So there's this DIAG protocol from Qualcomm, which is the diagnostics interface. There's another interface called QMI, which is the standard interface that, for example, Android is talking to, the iPhone also. And there has been also some fuzzing that has been done, but the big problem is that there is no full system emulation for these chips. And this is what our story is tonight. It's the adventure of pain that we will embark you on, as you can see, of reversing these chips. The gap that we want to fill is this gap of having fuzzing that is also using full system emulation on the hexagon chips. So this is what firmware is doing. Basically, you take the firmware itself and you emulate it completely as if it was running on the chip. So this talk is split in multiple parts. First, we want to introduce a little bit of how does Hexagon work and what is the ecosystem like, which phones is it running on. Then we will embark you on this adventure of the pain it is to reverse something that has absolutely no tooling, nothing works. So that's something that we will also explain. We will also have a little demo, and then we will give you the link to the tooling and call you also for participation. So Hexagon itself is a whole new CPU architecture, so it's not something that you would have like ARM or x86 or RISC-V, something like this that you would already know. It's something that has been created by Qualcomm, and it's specific for digital signal processors. So this is optimized to handle image processing, telco things like doing Fourier transformation and such. It has some quirky registers. We were laughing a lot when we saw that there's a chicken register. So yeah, that was quite a fun night. And also, to understand, it's also something that is a bit specific. It's not opcodes per opcodes, but it's packages of opcodes. So you can see here that we would have an addition, and then we would have a packet that runs in parallel up to 4 opcodes. So the architecture itself is quite weird, let's say. Obviously, all the tooling is proprietary, and also the OS is proprietary that runs on it. There is no really free tooling. There's some stuff on GitHub, but yeah, everything else is proprietary, as well as the SDK that you can download if you have an account.
Yeah, so we take you on the journey of our exploration. As Bruno said, so we have little shadowed pieces of tooling, and we stitch them together to get a full system emulation fuzzing. And for this we need an emulator, and we did a lot of reversing, so we need Ghidra in a later step. Then there's something called Clade. I will foreshadow a bit, you will hear about it. libfl we used for fuzzing, and then in the end it's a good harness actually. So for the emulator, first step of all steps is to get the actual firmware, then to get full system emulation somehow. And usually, if you get your generic full system emulator, then you will have to do some patching for your device because it's always a bit specific. So we begin with the firmware. In our case, and in the iPhone case, it's quite easy actually. So you can get the usual software update for your iPhone, and it contains the baseband firmware as well. So you can either use one of these mirror pages like this IPS m.me page, or you can also get it from the Apple CDN somehow, and then it's a small rotation of unzipping, grabbing, using file, and eventually you end up with a file which is a Qualcomm DSP6 executable, and in our case it's named the QDSP6 as WMBN. Interestingly, the process is very similar for other devices as well. For example, we looked into a router, a random 5G router, and also in the Fairphone, and it's relatively easy to obtain the baseband firmware because it's always part of the device's firmware somewhere. And then, as a little foreshadowing again, for the analysis, we looked into the strings of different firmwares. Here you can see to the left and down on the screenshot into a baseband, into a modem, into a router, sorry, and then into the iPhone. And we find similar strings there. The Squirtos string is something specific. It's Squirt OS is the OS from Qualcomm for these basebands. And these strings, we find them in the similar occurrences and like in the same order in both of the firmwares, which leads us to the conclusion that they are using the same SDK offered by Qualcomm, and which also brings us, like, it implies for us that if we find a vulnerability or an issue in one of these firmwares for one of the devices, it's probably applicable for other devices as well. This is really cool for like sharing code, but also sharing vulnerabilities, right? So having this firmware, we will go on and try to find full system emulation. And Bruno hinted a bit that this, like, the journey was like a lot of pain and a lot of like serious engineering work. But in this case, we quite got lucky. Like the default QEMU, it won't support hexagon full system emulation, right? So the hexagon soft MMU is not supported. But then we, like, just by searching through the internet, we stumbled upon something called the Qualcomm Innovation Center, and they maintain their own QEMU fork. And actually, in these forks, like in this fork, one of the branches, like they have like 120 branches, one of the branches has a system emulation for hexagon, which is work in progress, but of course we were going to check it out. So we downloaded and tried to compile it, and as most of the time with like open source projects, it doesn't work like out of the box, but after some like engineering again, we could run it. And then you can see the command basically down there in the black box, which is the command to just run our extracted firmware on a different computer, just to emulate it. Like, we were super happy about this. And then on the right, you see the 2 lines of bootlock we get with this. Very big success for us. And then it was only 2 lines. I will also show you a video of this after this. But we then also sneak peek into next step. We then reverse engineered the firmware and figured, okay, so we have 2 lines of bootlock. Probably there is more. So in the reversing on the right side on the decompile, you can see that right after the first lines, the CRUD kernel started and the CRUD kernel init cache params, like a bit later, there is another line which is supposed to become, it is called root task started. But we are not there yet, so we will probably have to debug some stuff to get to these next boot lines. Yeah, just to celebrate it with us, because we were very happy about this. The 2 lines of bootlock with the emulator here. Like, very good early steps for us. And then, yeah, I will take you on some debugging. So we can control the machine. We have the source code for the emulator, but we don't want to modify the firmware yet, right? So we know this is like we have QEMU logs, which is extremely helpful, but we don't want to modify the software. So we can use all the tools we have, which is in this case the logging and reading the source code. We had like what the usually flow of our like engineering process is there, that we run the emulation and then you see the 2 lines of boot logs and then you see, okay, it's stuck somewhere. Then we add some logging. You can see the param -d and then the MMU, which will give you all the MMU logs, in this case also the TLB logs. And then, yeah, we run with all the logging enabled and then go through the logs and see where is it stuck, why does it not continue. And this is like an example problem. We had different problems like this, but here you can say, okay, the TLB is trying to write to an index, or it's writing to an index which is out of bounds, and then QEMU is configured in a way that it's just writing to modulo that index, so it's overwriting a different index in your TLB, and this is in this way QEMU is not crashing, but the behavior is different that the firmware is expecting, right? So it's unexpected behavior in a way. And with the help of these logs and then also the source, we could figure out what is the max actual size of the TLB that the firmware is expecting. And then, because we own the source, we can change it. And so you see that there's a variable like num TLB entries, and we just change it to 56 entries, and then we can run it again. And with this, actually, like, it was very short, what I just explained to you, but you have to imagine, like, this is debugging of multiple days. But since you get all the control of the machine with this code, it's actually fun, and you can like work around it however you want. And yeah, so after these days, after the fix, we get more boot logs. Exactly 3, to be fair. Yeah, so we got another line, we fixed something, and then we have to continue. And then, yeah, what we did there is improve our Ghidra reversing to figure out what is there more to come? What do we have to fix?
Okay. So as we can see from the emulation, we only get a few lines of boot log. So we wanted to reverse the firmware to understand it better. And for reversing, we use Ghidra, which is a widely used reverse engineering tool. We can say we followed 3 steps. First was configure memory map, then compare the disassembly, and then train Ghidra. So first thing we do is open the firmware in Ghidra, and it doesn't work because Ghidra cannot understand hexagon architecture. So we have to use a plugin. So there are open source plugins available on GitHub. We have to compile the Ghidra manually with this plugin and then open the firmware. It's able to open it and read it. Then we see that it does not identify the memory segments properly. It does not understand what are the segments and what are the start address and end address of these segments. So this needs a fix. For this, we can use the memory segment information in QEMU machine, which is in the QEMU code, or since we already have an emulated firmware, we just run the firmware and get this information using this command M3. So you can see in the screenshot, we can see all the memory segments, we can see what are the start address, end address, and the size, and then we put this in Ghidra in the memory map, and then Ghidra is able to understand the firmware better and load it better. Then we want to validate that, okay, Ghidra can read this, but is it actually disassembling it properly, or what we see on Ghidra is actually correct or not? So we validate this with the Hexagon SDK tool. So if you have an account on Qualcomm Developer, you can get this Hexagon SDK tool, and this has a lot of binaries that can be used for debugging or reversing. One such binary is the object dump. So we disassemble the firmware using object dump, and we see it's really nice. We can see all the opcodes, we can see the packets, but then when we compare this with the Ghidra output, we see Ghidra is not able to identify the registers properly. You see this red label .000010, so Ghidra doesn't understand what it is, but from object dump we can see it's just register 1 plus 16. So we had to manually edit some of the register names in the code in Ghidra, and as you can see, this was a lot of pain. Then we decided that we have to train Ghidra manually. So first thing we did was refining the function names, because all the function names were just func 00 whatever, which does not help understand what the code is doing. So we went through the code, trying to read the code, see if there are any print statements, or if we can just understand what the code is doing, and then rename the functions based on our knowledge. So as you can see, a lot of our function names are like probably boot status related or probably task indexing related, but for some of the functions, we were also able to see from the print that, okay, this is what this function is doing. The next step we did was configuring the data structures. So from open source code or header files that are available on the internet, we were able to see the data structures, and then we can configure this manually in Ghidra in the data type manager. Then the third step we did was to analyze at the runtime, because we have the firmware running. We see that it is stuck, the emulation is stuck, and then we can see what is the register value at this point in boot, and then compare it with the Ghidra code, what the code expects the register value to be, and this also helped us to fix at the runtime. After a lot of manual training, we also thought to automate some things. So we captured the entire boot process in the QEMU, saved it into an output file, and then based on it, we created a Python script that just parses the boot logs and gets all the opcodes that were run. And then in Ghidra, it colors all the opcodes that were already executed from the emulation, and then we can see our Ghidra is much more colorful. Normally it's just white, but whatever opcodes are already executed, we can see it is green, so we can identify where we are in the code and which code is not covered yet. Then we also updated our script to support multi-threading, so now each thread execution gets a different color. And now we had a better understanding of the firmware. From the emulation logs, we saw 3 logs: cut, root started, root task started, and then from the Ghidra we can see after this there is something related to Clade, and this is where we are stuck because the next step is not executed yet. So next challenge for us is to understand Clade.
So when we arrived there, we were okay. You know, it boots. There's three boot logs that we have, but now we have nice tools. Now we can use Kemu. We can emulate the whole thing, and we can like debug. We can look at. We can compare that to Ghidra. It also has the same memory mapping. But now we arrived to something that was called Clade. I don't know what Clade is. So yet another thing that we need to fight. And we were Googling a bit around, and we saw that this is a compression algorithm. And how do we solve this? In 3 steps, we said, okay, first we need to identify what is compressed. We need to decompress it. And then maybe not. In the past, Qualcomm has, it's not the first baseband that they do, as you can imagine. It's something that is very popular. Like if you have an iPhone or a Snapdragon-based phone, you have this chip. So it's been going on since a long time. Before they had something called Delta Compress, and then Q6 Zip, and then Clade came. And Delta Compress, we have scripts on internet that can do this. Q6 Zip too. Clade also, but you need to find where the dictionary is. And there's like a register called config base where you can have like an idea where this thing is. And Googling a bit around, we saw that there is a patent that was filed by Qualcomm called Clade, cache allocated decompression something. I don't remember honestly. And it explains how it works. Even better, there is some help in the SDK. So we need to see, okay, what's the compressed part, right? And the compressed part, easy to see. If you run with binwalk, you can just see the entropy. So either something is encrypted or compressed here at the end, as you can see. And the SDK that we downloaded includes also a clade.so. And the funny thing about this is that it is the library to decompress Clade. Obviously, you need to know how to use it, and you need to find the config in your firmware. So we also saw that there was a Clade 2, and there's also the clade2.so, but this seems to be also kind of maybe hardware related. So also another thing that we need to take a look at. So we identified multiple segments that are compressed, and we were actually able to decompress one of them with the help of some people in the internet. And it actually works and fits quite well in our Ghidra. So if we import it at the right place, we see that there's code that jumps from there into actual things, and it seems to kind of fit well. So that's all good and all, but yeah, we only decompressed a small part, and as you can see, it's a gigantic part that is compressed, and probably there's some juicy stuff in there. But what if we didn't? What if we just skipped that and jumped over it, because we have control of the machine? And I mean, maybe we can boot the whole thing and some stuff will be in the compressed part, but we can take care of that later maybe. And if this is the stuff that we want to take a look at, then we can come back to this, but maybe we can advance. So what usually firmware and stuff like this and tools like this do is that you arrive to a certain place in the emulation, and obviously we're emulating it. So there's a lot of device that the firmware is expecting. You're expecting to have an antenna, you're expecting to have some clock, some timers, and things like that we obviously don't have. So a lot of stuff will not work. So what we just decided to do is we start the emulation, we emulate until we see that it's stuck somewhere, and then we analyze this part, reverse this part, and see, okay, why is it stuck, and how can we unstick it and just say, okay, I will write in memory what it expects to see, because it's waiting for a device to be online, so I can just say, yeah, it's online, continue. And with that, iterating like this, we were able to boot further. So to understand this, you need to understand that we were able to connect LLDB, which is like GDB, but in the LLVM world, which is also given by the SDK, and you can connect that to QEMU. So this is quite nice. You can connect, you can dump the memory, you can set the registers. So if you set the breakpoints at a good place and do what the firmware expects to do, you can continue booting. And finally, we were able to see actually some boot logs and not just 3 lines when doing this. And we see with their command sysstatus that we actually, if you see, like there's which we think it means user mode from the documentation. So it seems that the kernel finished booting, and the logs seem to kind of say the same. So researcher used control flow manipulation, and now we were able to have more boot logs. So that was quite nice. As you can see, I hope this is good. So you can see on the left here, we have LLDB that is connected, and on the right, you have the initial thing that we were seeing, so only 3 lines of boot. And you connect to LLDB, you see we are at FE10A3EC, and it's waiting for test bit R32, so it's waiting for this. And then we just do this. We just set 68 at this address, and we continue. And when we continue, we see, oh, lots of stuff is happening. And it's setting up the memory, and as you can see, it's like doing some memory pool, virtual address. So lots of stuff is happening, and finally, we are able to boot at a place, and you see app image in it. So in this place, you can see that it's finished the static mem. So the state that we are in is quite nice if we want to fuzz. So we are in the firmware kind of finished booting.
Yep, so we are basically ready to fuzz, we think. But also, as you saw, it still needs a bit of like manual labor. We had to define these LLDB macros and then like modify the control flow. We wanted to like improve this, so we thought about libafl, because this is basically what is also a state-of-the-art tool for coverage guided fuzzing with QEMU. And yeah, for this we had to merge with their code base, and then we want to use it to instrument our code, our firmware, and then search for a harness. Regarding merging, so libafl provides a component that is the libafl QEMU bridge. So it's basically their own QEMU, which is heavily modified to integrate with libafl. So it provides coverage, it has hooks, it has handlers for these hooks, and it also takes snapshots. Snapshots, for example, if our firmware, if we boot and then we want to take a snapshot at some point, then we want to start fuzzing, and at some point we want to roll back to a snapshot. We don't want to roll back to the beginning. So this is really nice for a fast fuzzing campaign. And then, yeah, the hooks definitely what you just saw, what Bruno did for the control flow manipulation. But also we can use it to instrument like any function that we want to look into in the baseband when it's running. The user mode is already implemented in libafl for Hexagon. So other people did this, but system mode is not there yet. One big problem is this libafl QEMU bridge doesn't have a common ancestor with our QEMU, like the Hexagon QEMU. So this was, and again, manual labor, quite a lot without Git. So how we solved this was basically diffing the bridge against its QEMU base version to get a patch out of it, which is just the libafl components of the what they implemented. And then we took this patch and threw it against the hexagon QEMU. And then again, a lot of like compiling issues, but after some engineering, we could get it run. And then we had a nice QEMU, like a hexagon-able QEMU with the integration of libafl. And then, yeah, we had to only add the support for the system, the full system emulation. Really cool tool, shout outs. Yeah, so for the instrumentation, it's Rust-based, so we can write our like full like start firmware and do hooks here, handle these here in Rust in one script, and also we can do introspection for certain functions. So imagine like task started, or you saw the print lines, we can just hook this and then read at the memory address that which is supposed to be provided for the origin function and do whatever we want with it. Because for this dynamic analysis, you saw this part of like trying to progress the boot and then going back to our breakpoints and handlers. We also added some like JSON configuration, so you don't really have to recompile it all the time. It gives you a much more dynamic like trial and error approach. And then yeah, basically with this config, like with this tool, we worked on progressing the boot to the state where we currently are. And yeah, usually it was using the colored Ghidra scheme to see where are we, then adding breakpoints, adding handlers to, like, I also know, like I also did some like firmware rehosting before. There are tools for this to automate this, or at least try to do it, but of course they don't work for Hexagon, right? So if anyone wants, please look into it. So we did a lot of manual labor. Now it's, in our eyes, easier to do it, but still, it's still manual labor, honestly. With this state, we are ready to fuzz, because we can, with libafl, we can also boot the whole firmware now. And this brings me to the topic of harness, which is also a hard topic, honestly. It's like 100 MB of firmware. We have like 70K of strings. We have 30K functions. Most of them don't have references. Also, this does not include the compressed section, so there's even more. So I want to give you some hints on like how we navigated this. Like cross-referencing to like source code that you can find on the internet is really nice, and also to the SDK. Like there are some code examples, and then you can see, okay, so they call grid init here, then they have like this in a follow-up, and then you try to find this in your disassembly to get like a raw overview of what is actually happening. We used Ghidra scripting quite a lot, as Rashna said. Like, so sometimes you have debug printfs, which then has the first param is like the file name, second param is the function name. So then we script down every call to this debug print. We want the second param to set it as a function name, just as an like to get like an idea, like get everything that we can basically. And lastly, there is the Qualcomm tooling. So if you have access to this, for example, there's QXDM, which gives you monitoring to the baseband, so you can attach it via the DIAC to your running phone. And then if you have something like the task manager, you can see it on the right on the screenshot, it gives you some details what is actually running on your baseband. And here we have the thread names, and these threads we can also find in our disassembly again. So then we can find some references like how are they named, where are they being started, where are they being created. Gives you some help to orient around. Yeah, so this is our current state. We are searching for a harness. Going back, I want to show you the whole instrumentation and running with libafl, but then, yeah, I will show the full tool after this. This is the configuration that we use, and you can see how we, yeah, have it everything nice in the JSON, and then we have a fuzzing mode, which will come after this. There are breakpoints defined, and then handlers. The handlers you code in Rust, but just where and which address they should be, like on which PC they should be called. And this is how you then start it. And the boot output. And you can see in the output, you see all the %x, %p, whatever, right? This is because we hook the print function. We don't get the actual output, but we hook the function, and we get, before it's even processed, we just get the string right from the memory. Yeah, so let's go to fuzzing.
To tooling.
So with all these challenges that we talked about, we are now ready to fuzz and ready to explore the unknown. So a little about our setup. You can see all of the challenges are now combined into one tool. So our tool has a JSON configuration file that we can use to set the fuzzing parameters, that we can also set the breakpoints. Then we have a harness where we define the first target and monitor the state and get the coverage feedback from libafl. Then libafl actually hooks into the firmware, does the function introspection, and QEMU does the emulation of the firmware, gets the coverage feedback, which is then given to libafl and back to our harness. And then we also have Ghidra scripts. So one that we talked about was coloring the trace of the boot and then putting it into Ghidra. Then we can show you a live demo of our tool. So this is how the directory looks like. We have the firmware config.json. So if you want to start fuzzing, you set fuzzing equals true. Set the first target address and the return address. This is currently, we have set it to a function that we see looks important in the firmware. And we set the return address, we set the QEMU arguments, the timeout for each input, and we also have the breakpoints. And to run the fuzzer, you just compile it using cargo build, and then it gives a binary, and then you can just run the binary. And as you can see, we get all the boot logs. We see the test case 1 started. Yeah. So this is the state where we have this app init done. This is the state where we create a snapshot so that the next inputs that we try, we don't start from the top. We run each test case from this snapshot. And now you can see like execution per seconds are pretty good. So this is our current state. Okay.
So basically that's it. Now we are opening up this and we are sharing all the stuff that we did. The idea is that we did all the painful stuff so that you can now find vulnerabilities and report them and don't have to do all the painful stuff. Now you have Ghidra. Now, I mean, Ghidra was already a thing, but you have these coloring scripts. You can use libafl. You can use QEMU, and it's quite nice to work with this. So you just create a JSON, you compile it once, and then if you want to just do some introspection, you just set breakpoints. You put fuzzing to no, and you see where you are in the booting process. You can compare that to Ghidra. You can export the logs and color that to see, okay, this is where we are stuck. And you can also fuzz. So the only thing that you need to do is to find a good harnessing point, and then you will be able to be up to speed, let's say. We will obviously also take a look at that, but there's plenty of code, 108 megabytes of firmware. There's also a lot of stuff that we still need to take care of. This clade thing, decompressing clade 2 segments, for example, is something that we have tried a bit to do, but we saw that skipping this was actually good enough for now. So this is also something that we need to take a look at. Once there's crashes that are found, you need to also be able to test it with like an SDR equipment, for example, or do some dynamic testing. There's also a lot of work that has been done reversing these protocols to communicate like DIAG and QMI. And this is definitely something that is easy to fuzz now because you have coverage guided fuzzing. So you can just hook the DIAG queue, and then you can fuzz this. Integrating with firmware would be also quite nice because this is like a more mature tool than ours. And obviously, would like to thank a lot of people who were very helpful in all the parts of this talk. And yeah, please scan the QR code and use our tooling.
Okay, thank you very much. And are there any questions here? If not yet, I have one. You said you used the iPhone or the firmware you found in the iPhone update, and that you found other baseband firmwares in other packages. Did you try them with your tooling as well, or is it something that you still have to look into?
I mean, yes. We also try to run the router firmware, like the baseband for the router, and also the one for the Fairphone. But it's then the manual labor currently to progress this boot procedure to also make it usable for other firmware. Like, this is a step that is currently really labor hard.
Okay, so they differ a lot in that area.
I mean, at least the offsets probably, but some things you could maybe generalize would be nice.
Okay, thank you.
Hi, did you know if and how often Qualcomm updates the firmware?
Honestly, no. I think that, I mean, it's a huge code base, so I would expect it to be updated. But if we compare the SHA-256, probably they differ. Yeah.
I know that we at least have 2 different versions in the recent year, but just because I stumbled upon this, not because I checked actually.
What we can say about this is there's a lot of code sharing for sure, because if you compare the router firmware that we had and the iPhone one, if you grab for the strings, it's in the same order, the same string. So there's definitely some code sharing.
Okay, if there aren't any more questions, then thank you very much again, and give another round of applause, please.